Good morning, everyone. First of all, it's our pleasure to have had the chance to participate in this conference. I am Sarah Boudou. I'm a PhD student in University of Lagos Lab, Algeria. We will have a sneak peek to our work titled Breast Cancer: Deep Transfer Learning Techniques for Breast Tumor Detection in Mammography. With an estimated 2.3 million new cases, representing 11.7% of all cancer cases, in 2020, female breast cancer does replace lung cancer as the most common type of cancer worldwide. Breast cancer is the most common form of cancer among women, accounting for 1 in 4 new cases and 1 in 6 cancer-related deaths per year in the vast majority of countries. There are several imaging methods that can be used to detect breast cancer. The most commonly used strategy for identifying suspicious lumps is mammogram imaging, which enables radiologists to spot abnormal masses. However, it can be challenging to interpret a mammogram since the ability to identify lesions depends on the radiologist's degree of expertise as well as the image quality, which can result diagnostic errors. The poor image quality, eye tiredness, or radiologist oversight are the main causes of the rise in abnormalities detection failures in mammograms. Therefore, it is necessary right ones to support medical professionals in identifying and detecting breast cancer, as this will accelerate the diagnostic process. In our presentation, we will cover the state of the art, then after that present briefly our approach, and finally we will have a conclusion. So there have been several studies published on the issue of breast cancer detection and diagnosis, yet we will emphasize on those that conducted the detection using mammogram images. This falls under one of the 3 categories. First, breast tumor identification, which classifies mammogram images as either normal or abnormal, and it is a binary process. Second, breast cancer detection, which is accomplished by classifying normal, benign, and malignant mammograms, is a multi-class process. And finally, breast cancer detection as well, which is also a binary classification, but just for tumor cases. So the classes are benign and malignant, which is out of our topic today. So in order to confirm the presence of a breast tumor, a binary classifier containing normal and abnormal mammography is required. To do so, the model must be able to distinguish between normal and abnormal breast tissue. Thereby, the region of interest in this situation is the whole organ. On the other hand, in order to detect the tumor's type using a binary classifier with the benign and malignant mammogram images, the ROI in this case is the tumor's area, so we don't need the whole mammography as an input. Therefore, in order to have a breast cancer detection model with a high accuracy, we first need to have a tumor detection model, which is reliable first step. Then a second one for tumors type detection can be created based on the previous model. This was the fundamental drawback of various earlier studies that used a multi-class classifier to address the issue. So, according to the preceding, we aim to propose an accurate breast tumor detection model as a first step into cancer detection. In our proposed study, instead of using the commonly used small database, the Mini-MEAS, we took samples from 2 different databases in order to guarantee diversity in the images, balanced data, and a bigger amount of it, which leads to a well-trained model. In addition to that, we use transfer learning and data augmentation techniques to prevent imagery overfitting, problems using three recent modified pre-trained convolutional neural networks, exception, VGG16 and ResNet 50 version 2, with and without trainable layers for several trials with several hyperparameters. So in our approach, first of all, as mentioned before, we gathered data from two databases to avoid the problem of imbalanced data with which could affect the accuracy. The first one was the Mammographic Image Analysis Society database. Taking the whole database as a sample will be 207 normal images, 115 abnormal ones, including benign and malignant cases, and that will make the total number of 322 mammogram images. And the second one was the Chinese mammography database, which includes just abnormal cases, where 92 missing abnormal images, mixed benign and malignant, were added as a sample from this database, covering the shortage of images in the abnormal class. That made the total number of images in each class equal. The gathered mammogram images were pre-processed using several filters in order to extract the region of interest, which is in this case the breast area, and remove the noise as well as the background. So first, the binary filter was applied to the images, as you can see an example from each database. Then the resulting image was used to detect the largest blob, which is the breast area. And by multiplying the new resulting image with the original one, all noise will be eliminated and we get only the organ. But since the Chinese mammography database images does not have any noise except the background, the process was easier there. Next, we have the Wiener filter, which we consider as a noise removal filter. Using it allows us to eliminate any remaining noise. After that, the objective of contrast enhancement is to improve the imagery low contrast of mass pixels. Therefore, it is used in images that include abnormalities. So to accomplish that, we use the contrast limited adaptive histogram equalization, the Clahy filter. So after that, the data was split randomly into 75%, which is 310 images, 155 image per class as training set, 5%, which is 20 images, 10 image per class as a validation set, and 20%, which is 84 images, 42 image per class as a testing set. To guarantee an accurate evaluation to our models, we reduced the amount of data in the validation set and add it into our testing set. Next, data augmentation technique were achieved through simple modifications such as horizontal flipping, zooming, and so on. We used it on the just training set, of course. After that, the fine-tuning phase is done. So, as mentioned before, transfer learning is considered as a useful tool for problems where the dataset is not large, so we adapt a pre-trained model to our situation. As mentioned before, the three pre-trained CNNs were exception VGG16 and ResNet 50 version 2. So, the transfer learning techniques are based on transferring learned knowledge that has been trained on a very large dataset, such as ImageNet, to any problem that have a small dataset. We can so gain a great CNN architecture, variable weights that we could use as they are by freezing the layers to not train, or use them as initial values to our problem and enable the layers to train, or of course not use them at all and start from scratch the training process. So in order to adapt and build each model for our problem, the selected pre-trained models were imported with the weights of ImageNet as initial weights, with an input shape of 224 by 224, and without including the top. It signifies, of course, that we excluded the fully connected layer at the network's top, so include top was set to false. After that, a global pooling layer was added after deleting the softmax output. Of course, for some trials we used global max pooling, and for others global average pooling. So global pooling is an approach used in traditional CNNs to replace fully connected layers. The key principle behind global pooling is that one feature map should be constructed for each matched class of the classification task across the final convolutional layer. Rather than building a fully connected layers on top of the feature maps, we take just the average or max, depends on which global pooling we are using, of each feature map and feed the resulting vector directly into the softmax layer. Of course, in our case, it's a sigmoid layer. So, the global pooling layer was followed by a dropout layer with different values from the range of 0.2, which is 20%, to 0.5, which is 50%. And lastly, because our case had a binary classification, we introduced one output with a sigmoid activation function to adjust the models to our situation. As you can see, an example of one of the selected models, the exception. Finally, all the models were evaluated to determine how accurate they are, and the obtained results from each one were compared to each other in order to determine which one is the most suitable model for our case, as well as the main criteria that could influence the results, and which hyperparameters of each pre-trained CNN model are suitable for our situation. We were able to determine the accuracy, sensitivity, specificity, and the area under the curve based on the results from the confusion matrix and the ROC curve of each model. From the obtained evaluation results, we can declare that using a pre-trained model without enabling the layers to train will not achieve great results, as opposite to allowing them to do so. Yet, in our case, it is clear that the exception with trainable layers had 99.9% accuracy, which made it the most suitable model for our breast tumor detection case. Meanwhile, the others also achieved good results compared to the previous studies. And from the obtained evaluation results, we can declare that we accomplished our goal by creating an accurate breast tumor detection model, as well as improving the reliability of the proposed pre-processing phase. However, when compared to previous studies, especially the studies which were in the same context of ours and used the pre-trained models, our results were way better, as you can see in the table. So, to sum up, the results of this study shows an accurate breast tumor detection model, which proves that our approach was useful. The exception with trainable layers had the best results among the others with 99.9 accuracy, which makes it the best pre-trained model for breast tumor detection with this dataset. And we managed to prove also that using a pre-trained models without training the layers is not useful in our situation according to the results. And accordingly, the chosen filters in the pre-processing phase were well suited to our situation, putting our approach ahead of the existing ones. As for future perspectives, adding another database to the collected dataset may have better results, since using two achieved great results. We can, of course, test the proposed approach with the GPU in the training phase, since we just did the training with the CPU. And finally, and the most important, since the obtained models were accurate, especially exception, which could be useful as a solid first step for identifying the specific types of abnormalities, such as benign and malignant, it dives even further into the subtypes of a single kind, such as masses and calcifications. Therefore, we can assert that what we accomplished could be used as a starting point for future research. This could help achieve better results in breast tumor type detection, and that leads to an accurate computer aided diagnosis systems for breast cancer. Of course, we can consider also using the proposed approach for other cancer cases or types, such as brain cancer, for tumor detection as well. Thank you for your attention. Happy to answer any of your questions.